Now, in this particular video, we're going to dive into the mechanism for a Bronsted-Lowry's acid and base, just a little bit of a refresher from various lessons that you may have come across at school. We know that a Bronsted-Lowry's acid is an acid that actually donates electrons. So in this case, protons, not electrons. Be aware of that. That is a huge difference between Bronsted-Lowry's acid and that of the other one that we're going to dive into, which is a Lewis acid. Lewis acid deals with electrons, however Bronsted-Lowry's acid deals with protons. So in this case, we are focusing on the most important, which is a proton donor. However, for the Bronsted-Lowry's base, we recognize that they are a proton acceptor. Once you're able to recognize these particular facts, you can actually apply that to a specific question, which says that you should show the mechanism for hydrochloric acid reacting with water. Now you notice here that for the reaction we have HCl actually reacting with water, and once you see this, you actually be like, oh, by the way, this is an acid. Of course, everyone knows that. So in this case, by convention, we know that this is a Bronsted-Lowry's acid. We expect this to actually donate protons to its Bronsted-Lowry's base by convention right here, and for some reason we expect our product to actually have a hydronium with a positive charge and that of our chloride, which has a negative charge. So now you see this reaction, you're wondering what is the mechanism for this particular process. So to show the mechanism, first step is to draw the Lewis structure of all the compounds and ions in this reaction. Now the first one here is just a hydrogen bonded to chloride, and what happens is that, you know, chloride has lone pairs around it, and this is actually satisfying the octet rule. Now going to water, we know that water is bent with oxygen forming a bond with hydrogen and the other hydrogen, and you have your two lone pairs on the oxygen. And then for your product, we have an hydronium with a lone pair, and it says a positive charge, and this positive charge on the oxygen is due to the fact that the former charge is created by 3 bonds around oxygen with just one lone pair on that same oxygen, creating a positive charge. And finally we have chloride, which has 4 lone pairs, thereby causing it to have a negative charge on it compared to the neutral form when chloride bonds with one particular atom, like for example hydrochloric acid. So once you notice this, your next step is to observe the movements or positions of atoms. So looking at water here, you actually notice that water actually accepts a hydrogen atom from our reactants right here to actually form this particular compound right there. So this compound is known to be a hydronium ion in this part, and as a result, since you're able to observe that, we can write that down. H2O in this case actually gains a hydrogen atom, or I will say a proton, from HCl to form a hydronium. And another observation you can make here is that the chlorine actually loses a proton, and this actually leads to the formation of a chloride with a negative charge on it. So you can see the observation, and based on these observations right here, we can actually come to a conclusion on the mechanism and showing the electron pushing arrows. So in this case, once you see oxygen right here, oxygen contains negative charge electrons. So this negative charge electrons causes this particular oxygen in water to actually be attracted to the proton on the hydrochloric acid. And so what that results in is that this is actually caused by the charge or dipole moment that is present not only in the acid right here, but also importantly the base, which is a Bronsted-Lowry's base. So this actually shows that as a result the electrons will actually go as the electron curve arrows from the oxygen lone pair to the hydrogen on the hydrochloric acid, and then this bonding pair actually cleaves and forms a lone pair on our chloride. So as a result we actually get our product, which is what we have right here, where we have our hydronium and we have lone pair on the oxygen, and then we have the other hydrogens right there, and then finally we have our chloride sticking out with a negative charge right there. So that is about it for creating the mechanism and analyzing the reaction based on what is given in the question. And a little challenge question here is to actually determine the mechanism for this particular reaction, where we have a form of a triethylamine, and this is going to be reacting with a specific type of carboxylic acid right here. So I'll give you guys a couple of minutes to analyze this and then come up with an answer right here. 1, 2, 3, let's go. So in this part you notice that oxygen will have lone pairs right here, 2 lone pairs, and this other 2 lone pairs right here. And so what we see is that, hey, since in this case we have a hydrogen sticking out right here, this hydrogen will make this particular compound right here to be a Bronsted-Lowry's acid, and by convention this will actually be a Bronsted-Lowry's base. So as a result of that, we expect our Bronsted-Lowry's base to actually have a lone pair that actually comes in and pick up our hydrogen atom there, and then this hydrogen oxygen bond here cleaves and forms a lone pair on the oxygen. So as a result of that, what we get as our final products is as follows. We have with the positive charge on the nitrogen, and we have our other substituents attached to the nitrogen, and then on our other side we actually form our other product right there, where we have a negative charge on the oxygen right there. So that's about it for this particular video. Hope you're able to understand this. Hit a comment down below, let me hear your thoughts about these examples and this little challenging question that we worked on together. All the same, stay smart and believe in yourselves.